Today we are going to talk about some side channels. So we have seen before that if you have memory safety bugs, some unchecked printfs, you can get code execution and stuff. That's problematic. But what if everyone just uses Rust? Everything just disappears. Everything is perfect now. We all use nice LLMs instead of the shitty ones. And all of the logic bugs also disappear. So also the crypto exploits just don't exist anymore. Everything is safe, right? Well, not really, because side channels are still an issue. And they can exist even if a program is logically and memory safety-wise completely OK. So about me, who am I? My name is Weissteiner. I am a PhD student at the Institute of Information Security at the Technical University of Graz. And my research area is side channel attacks and defenses. This is very broad, since you will see this is a very broad field. And I'm, in my free time, interested in breaking systems that annoy me, which is why also our sysadmins really like me. So let's start with the basics. What is a side channel? Let's look at some real-life examples. There is dirty dishes in the sink. Your roommate probably made some food, right? Makes sense. If on Monday people are coming in and see stacks of 25 pizza boxes lying here around here, there was probably a CTF. The hood of a car is hot. It's probably recently somebody was driving. This is all probabilistic information. So this doesn't need to be true, but it's very likely. So this essentially is a side channel in real life. If we look at code, we have a really simple example of a pin check. We have the correct pin 1, 2, 3, 4 here, and some input. Whenever you input a pin, this loop checks against the correct digits, and if the number that you entered, if the digit that's currently checked does not match the digit of the correct pin, it exits early. Some of you may already see the issue here. If we measure the execution time of this thing, the correct pin is 1, 2, 3, 4. So we put in 0, 0, 0, 0. It's going to be pretty fast. If we add a 1, it's suddenly slower, because now the first digit is correct, and we have a longer runtime. For all of the other ones, it's going to be fast again, because the first digit doesn't match. And so on. So now we know which was the correct first digit, because the execution time was longer, and we can recover this in 10 tries at max. We can already stop after the second try here. We can do this again. The first digit, we know it now. This is going to be about the same length. These are not correct. When we hit the correct second digit, suddenly it's longer again. The other ones are shorter again, and we just repeat that digit by digit. And the longest execution time that we can get is the correct pin in the end. So when we have a maximum of 10 measurements per digit and 4 digits per pin, we break this in 40 tries on average. No, worst case 40 tries actually. On average, we break it in 20 tries. Brute force, it would be 10,000 tries. So even in the worst case, when the pin is 9999, we just sped up our brute force by a factor of 250, which is great. So let's try to define a side channel. Side channels are sometimes a bit hard to define. This is one definition that I would say applies mostly. It's usually implementation-defined behavior, because the side channels are usually not included in the protocol as a thing that should exist. It measures some side effect of the program execution, like the runtime. So we gain metadata about the execution of a program. We interact with the victim program as a normal user. So we are not printing, I don't know how many thousands of spaces to get some override in some variable. We are just inputting pins. This is what the program was designed to do. And this means we can now attack correct code that is functionally correct to still break it. There are a bunch of different things that we can measure to gain side channel information out of. execution time we saw already. There is memory usage. Maybe some code path allocates more memory than a different one. Power consumption is a popular one. Electromagnetic radiation has been shown before. People have recovered screen contents from electromagnetic radiation. Acoustic signals also exist. Yeah, there's many, many more. Anything you can think of. A really popular branch of side channels are the CPU side channels, the CPU cache side channels. So talking about caches, caches are very small, very fast memory that you use to store data to speed up recently accessed data from a slower memory. For example, in the CPU, we have multiple layers of caches, each smaller and faster than the previous. Yeah, this exists in a CPU, this exists in hardware, this exists in software. And of course, speed up recently accessed data, we can already see a timing side channel in here, right? There's multiple techniques that you can use. Generally, flush and reload is the simplest one. You access data, and then you flush the old data, and you try again. We will see that later. There's also evict and reload, flush and flush. There's multiple different techniques that apply essentially across the board with everything that has caches. If we look at flush and reload in the context of the CPU, we have two processes. We have a victim on the right, we have an attacker on the left, and they both map the same shared library. They have some shared address. And if this address is cached, it's fast for both of them. This is the point of the cache, so everyone gets a speed boost. Now, what the attacker can do, it can flush this cache line from the cache. Then it waits a bit. If the victim now accesses this cache line, it's back in the cache. And whenever then the attacker can reload the data, time how long it takes to access this data, and can know whether the victim accessed this specific address. So this maybe looks a bit abstract. So let's look at assembly code, the least abstract thing that we can have. This is how you measure timing very precisely on Intel CPUs or x86 CPUs. We need the M fences here. These are essentially a barrier preventing the CPU from reordering instructions, because we don't want the CPU to think this measurement instruction should go after the memory access. That would be bad, because then we would measure nothing. So we have the fences here. RDTSC reads the timestamp counters in these two registers, arrayx and RDX, and the OR operation and the shifts just assemble the timestamp counter from two 32-bit values to one 64-bit values. You don't need to follow this, just know that this gives us very accurate timestamps as a function. And what we can now do is we just start a measurement. We get the starting timestamp. We access some address, and we get a second timestamp. We calculate the difference. Then we flush the cache line. The difference between the timestamps is then how long it took to load this data. And if we measure this for cache hits and cache misses, we get these nice histograms. We can see, although cache hits can sometimes be slower, maybe due to scheduling or any other interference, no cache miss can ever be faster than this barrier here on this machine. So we can classify cache hits and cache misses very efficiently by just saying, OK, everything smaller than this, like 200, let's say, is a hit. There are some restrictions to flush and reload. For example, you need some shared memory. If you cannot access the same memory, this doesn't work. We also need a high-resolution timer. Luckily, the read timestamp instruction is just unprivileged. But it may not be available, for example, in JavaScript. But there are tricks around that. But this is out of scope of this talk. If we are just running on a different core, it may be hard. So if we are targeting very fine-grained access patterns, it may be hard to hit the right timing. So you might need multiple measurements. So the precision is good, but not ideal for very, very tight loops, for example. So what can we do with this? We can, of course, now find addresses that leak something. We can decompile a shared library. We can find interesting instructions where it accesses something based on some condition. It has also been shown that we can just do automatic templating. Has any one of you ever used Cheat Engine? So there you essentially you scan the memory, you take damage or whatever to change the value that you are looking for, scan again, until you are narrowed down to something that is kind of the right address for cheating your health values. Similarly, we can just run flush and reload of an entire program or shared library while we do the thing that we are trying to track. We just count how many cache hits we see, and it is likely that one of the addresses with many cache hits is the one is somehow correlated to the action that we are taking. And we just have built a template for the attack without having known anything about the program at all. And I can show you this, actually. So, yeah. So I have prepared gedit here, which is just a text editor. We can get the memory mapping. This is fairly small. Essentially, we get this path of the gedit shared library. I've prepared this command. It's not that important. We just need one of the shared libraries. We could try all of them. This is one that works. I tried this out. But before we do anything with the shared library, we need to find out what the threshold of cache hits and misses is for our system. And for that, we have a small tool that we can run. It just classifies cache hits and misses and prints something like this. And this is just a bunch of numbers. This maybe looks kind of familiar to the histogram that we showed before. We have a bunch of large numbers here, and then a different distribution here. So we have the cache. We just counted the timings for cache hits on the left and cache misses on the right. The specific numbers do not matter. We can just see that at 2:30 here, there is no cache miss that's counted here, and most of the cache hits are below that threshold. So we can just choose 2:30 as a value for our attack, which is the number of cycles that a cache hit, that a cache miss can't go below. A cache miss can't go below. Great. Then we start the profiling step. We use our 240 number. And here the 100 is just seeing how many times we try to flush and reload. This just sets the speed. We can run this now. And if I now hold A in the program, yeah, there's a bunch of zeros here. OK, seems like we got most of the program. We can now scroll up and see where we got cache hits. I can zoom in maybe a bit. Great. There's many, many zeros. Oh, this did not work, apparently.
It did. It was one.
There was one. There should be more. Well, let's just run it again. It's the demo curse. Delete this. Run it again. Yeah, there were some values here. OK. Now there's a 1. I tried this before. It was like 20. But let's just try this address. We got one cache hit here. Maybe my laptop got a bit hot. I did not prepare the laptop specifically for this. This is just with Turbo Boost enabled and everything. Can be a bit sketchy. So we now run the exploitation part with that same threshold value and the offset inside this program. And hopefully, we can see some cache hits when I'm typing. When I'm not typing, nothing happens. When I'm typing, we see some activity. This should usually work better. Maybe, yeah, maybe the laptop just got a bit low on battery. I don't know. Anyways, the demo gods did not like me today. Anyways, with this templating, you can, or with this side channel in general, you can track a lot of stuff. We saw keystroke tracking, which there is some papers that show that with statistical analysis, you can, from keystroke timings, recover whatever you typed in some cases. People have attacked AES-T tables, so you can recover from AES encryption the key by tracking which parts of this lookup table were accessed. People have recovered RSA keys with this by tracking the execution of a square multiply algorithm. And there's also ECDSA keys that have been recovered, website accesses, stuff like that. So by just this very simple attack, we just track access times to addresses. We can already do a bunch of stuff. And we can also use these side channels as covert channels to communicate data covertly without anyone noticing, hopefully. For example, if we share some large array between two parties, process 1 runs flush and reload over the entire array, checks which parts of the array have been accessed. Then process 2 can just encode bytes via an array access. For example, by just accessing an offset in the array depending on a byte value. Process 1 then sees a cache hit on only that specific value, and information has been transmitted. What if we do this? We access an array based on some value behind a kernel address. This should fail, right? But if the CPU manufacturers haven't been paying attention, the CPU could already execute parts of this instruction and already prefetch some stuff into memory. Then the permission check, of course, fails. I do not have access to kernel memory, but, and we get an exception. But we already have stuff loaded into cache depending on the secret value from the kernel. And this looks kind of bad. And it was. This is exactly what Meltdown did. We had this small bug in the CPU that caused it to load stuff into the cache too early. And by encoding this into the cache, we could leak arbitrary kernel memory. This has luckily been fixed on all of the CPUs, I hope. But this shows that cache covert channels, so cache side channels are not just an attack primitive or an attack by themselves, but they can serve as building block. So most of the transient execution attacks, Meltdown, Spectre, rogue in-flight data loads, and Fallout, many, many more. These all came out in a short time frame, like 2016 and on. They all worked by somehow tricking the CPU into loading stuff into the cache, even though it had no permission, so even though the user had no permission to read that data. So CPU caches, yeah, sure. What else can we attack? Because CPUs are very low level. Most of you probably do not write assembly on a daily basis. We have some very trivial ones. The DNS cache, for example. Some of you may have had to clear the DNS cache because something in the networking was wrong, because DNS always breaks. The OS caches old domain names that you accessed previously. So naturally, accesses to previously cached domains are faster. This is the point of the cache. So anyone who can do web requests on your system can essentially see what websites you accessed recently, irrespective of whether you use private browsing modes or a VM or something like that. We saw that we can evict the cache by just resolving so many entries that there was not enough space for the old ones, or by just sending some invalid messages, responses to the receiver on Linux. Then it just flushed the cache by itself, which was very convenient. This even works from the browser, and it even works without JavaScript. So there's no code running on your machine, and I can still see what websites you accessed recently. The scriptless attack works by defining a font. We load a first URL on our server to start the measurement, which takes some time. We then load whatever target domain we want to have. Depending on whether the domain is cached or not, the access will be slower or faster. We access the second domain, and by timing the time between the two domain accesses, we know whether you accessed this recently. Could be pretty bad, depending on what you did in the last 10 minutes. Similarly, another software cache that every one of you has on their system is the OS page cache, which is used to load stuff from the disk into memory. So when process A needs this shared library, it gets loaded into memory once. Process B just gets it from memory again, which is again faster. You get the gist now. It avoids slow disk accesses, speeds up the disk accesses by like 50 to 400 to 500 times. There's a times sign missing here. And is of course shared between processes. No CPU defenses help against this. This is software only. This works on ARM as well. What they did with that is they could track the presence of pkexec. So if pkexec is the tool that pops up sometimes when you want to start some program that requires root privileges. It pops up, asks you for your password. By tracking the page cache, they could detect that you wanted to start this program in 800 nanoseconds, which is less than 1 frame. So they could draw a fake password prompt over your real pkexec window before it was even rendered, and steal your password. This works on latest KDE Plasma. It also works on SteamOS, funnily. Website fingerprinting, yes. We can track some Firefox shared library depending on what your website does. If it plays a video, if it displays some pictures, we can see what website you are accessing. And we can classify this with like 90% accuracy, which website you are accessing, while we are just accessing some shared library from the page cache. So what can we learn from these cache attacks? Caches are really useful to improve performance, and they're required. If your page cache on your system didn't exist, everything would take 500 times as long. Everything is super, super slow. But the trade-off here is that wherever there is a cache, there is timing leakage. And we need to be aware of that. And system designers also need to take this risk a bit into account, maybe give the users options to choose between security or performance here. Now, let's go away from cache side channels. You can all open this website really quick if you want to. No data is saved, no worries. And once you have it open, you will see on the left side, there's a picture slowly, slowly loading. If you start the video on the right, please turn off the volume. I don't want 10 videos playing at the same time. You can see that on the left, the picture changes. That graph that you see is getting some more activity. This does unfortunately not work as well here in Eduroam because the internet connection is quite fast. But on private internet connections, this is very, very visible. Does anybody see a good signal? Yeah. What we are exploiting here is this last mile bottleneck. So on the internet, all of the backbone routers and all of the big servers are connected with really, really strong connections, capable of multiple gigabits. And because usually the users are the weak link here. Your provider does not give you 10 gigabits. They probably give you 100, maybe 300 if you pay a bit more. Anyone that has played online games knows this behavior. If you are downloading something in the background, the ping increases. So if there's nothing in the download queue, the connection is idle, you get your packets immediately. And the more other data is in this process of being sent and received, the ping increases up to almost dropping out. And this website that you have open right now sends you 1 byte in a TCP packet, waits for the acknowledgements, and times the time difference in between. It does this again and again and again, and renders this graph to your device live. When you take all this data and you chuck it into some machine learning, you can see what websites the user is currently accessing while they are loading this picture. You can see what video you are watching while you are loading this in the background. And I can send you a huge, huge image file that just downloads for 30 minutes in the background in some random tab and can monitor you as long as I want. This does not require your router to respond to pings. This bypasses CGNet. You are the one downloading from me. So this bypasses a lot of security features of the internet. You just need to click on some website where I have embedded some resource. So we can see here that also contention of a shared resource, like the internet connection, can leak a lot of information. And neural networks are really strong to extract data out of seemingly nothing. And this side channel in particular is completely independent from hard and software. This is just a fact of how internet connections work, how Ethernet works. And other contention-based attacks include, for example, CPU scheduler queues, where they scheduled a bunch of multiplication instructions to track whether other hyperthreads on the same core were also multiplying something to recover cryptographic keys. DRAM also has contention. This is commonly used for rowhammer research to reverse engineer address mappings and stuff. Because depending on whether addresses collide in the DRAM, it takes longer to fetch different sets of data, depending on where on the DRAM the data actually resides. Also, SSDs have been shown to leak a lot of data just by contention. And with essentially all of those, you can fingerprint whatever website a user is accessing. Yeah, my LaTeX failed here. This is super hard to mitigate because many of those contention effects are just a fundamental fact of the device that you're using. Your SSD cannot provide you with more data rate. You're maxing it out. And apart from leaving half of the speed for in case somebody tries an attack like this, there's not much you can do. But why do we care about these website visits? I have been talking about website fingerprinting for a long time now, many times. Advertisers really like to know what stuff you're looking at. Some governments might really want to know whether you are maybe a member of the opposing party and have been to their website recently. Scammers also really like to have a lot of information about you. Has any one of you ever received an email like that? Like, hey, I saw you, I hacked your computer, you have been watching these videos, I have filmed you, pay me money. These are not that uncommon, but they are obviously scams, right? They know nothing about you, they just say like, yeah, you probably have watched something. Imagine the email looks like this. You access this website at this time, and this is actually correct. You're getting scared now. Much more likely to pay. Even worse, this website. So yeah, even though this is not like remote code execution and stuff like that, these attacks can really degrade your privacy, especially when the adversary can be even stronger than just some guy hosting a PNG on a server. I'm also going to talk about power side channels really quick. This is not my area of expertise, but they are super, super interesting. The power consumption of a CPU depends on the instruction it tries to execute, and sometimes even the data. And you can, if you measure the power measurement, if you measure the power consumption in a fine-grained enough way, and you measure often enough, you can start to extract secret keys from algorithms again. Of course, if you want to measure with a physical probe, if you want to add a multimeter to your computer, that requires physical access. I can just open up the computer, take the hard drive, have all the secret keys. But it has been shown that software interfaces like the running average power level, the power limit, allowed users to just track the power consumption of the CPU in a detailed enough way to just run these attacks from pure software. Since then, this interface has become privileged, so this is fixed. But there have been other papers that just bypass this limitation by going via one more level of indirection. For example, they look at the core frequency. If you pull too much power, the core needs to throttle down because it's getting too hot. The frequency of your CPU can leak stuff about what it's doing. The temperature, same thing. When you calculate too much stuff, when your instructions are too high power, the CPU gets hot. There has been a recent paper from a colleague of mine who looked at the interference between the CPU power and the magnetometer of an Android phone. And you could see when the CPU started to draw a lot of power, the magnetometer just turned a little bit. And that was enough to also steal pixels from the screen. There were papers that recovered power-related signals by listening to coil whine via the microphone, even I think even across Discord calls or something. So there was a paper where they could cheat in video games when you were in a call with them because they could listen to the sounds that your computer made while playing it. So even this might seem very inconsequential, but there's a lot of information if you just know how to extract it. And yeah, the key insights of this whole thing is power side channels in general can be inherent problems of a system. You are not getting away from the fact that the CPU generates heat when it does something. There are some techniques, constant time implementation techniques, that help you mitigate the impact of such vulnerabilities. Constant time also means, for example, constant memory accesses. If you have, in a non-constant time code, memory accesses depending on a key, in a constant time application, you would just access all of the possible memory locations, so there's nothing that can be leaked, hopefully. But they are often very unrealistic. If you think about the pin example, of course, like we can calculate 4 more digits. That doesn't cost us anything. But if we have like a 5 gigabyte file and we want to compare 2 files, and we know after the second byte that they are not the same, it's kind of a waste to just run over the entire file and waste all of that time. There are some other options for some of the attacks. For example, power side channels can be sometimes reduced by masking the secrets. There is the possibility of adding noise, but that does not fix the problem. It just makes it harder. Artificial delays, it's the same. It makes everything slower and also doesn't really fix the problem because probably the underlying leakage is not gone. The mitigations often come with big drawbacks. And there is a trade-off between usability and privacy, usually. And this is made even more interesting by this new thing called confidential computing. Because like previously, if you hosted the server on, I don't know, Google Cloud, you trusted Google to not access your data. Confidential computing tells you, okay, you're now so securely encrypted, not even your hosting provider can see that data. This trusted execution environment is protected from the host OS, and it is guaranteed by the CPU vendor, guaranteed in a way, like they tell you that you are completely secure against attacks from the hypervisor. Current implementations of this are AMD's SEV, there's Intel TDX, and hopefully soon there's actual chips with ARM CCA, where you run just a normal VM in this confidential environment. And there's some cryptographic attestation so that the hosting provider cannot trick you into doing, into thinking that you're actually running inside this environment, but you're actually not. The cool thing about these new technologies is that now the threat model completely changes. Previously, all of these kernel-only interfaces, they were not interesting, because if you have kernel permissions, you can see anything, everything on a system anyways. But now we own the system, and we attack some part of the code on our system, while we have kernel privileges, physical access, and everything we dreamed of previously. So now, suddenly, features that previously did not matter in a security context can be exploited. There are architectural attack surfaces, like if something is implemented wrong, obviously. If there's a bug in the confidential computing setup, you can break it. But there's also new side channel opportunities, for example, performance counters. They are privileged counters that count certain events on the system. So because they were privileged previously, they did not matter at all. You had kernel privileges anyways, but they were also enabled while running the confidential VM. So by interrupting the confidential VM very frequently, every instruction, and just tracking the performance counters, we get really deterministic information leakage out of that. And with this, we broke RSA, we broke TOTPs, we extracted secrets from TOTPs, we broke some post-quantum crypto. And the inside of this is that if you change your threat model, if you now say, okay, now the machine owner is malicious, and that's a valid threat model, suddenly you need to rethink a lot of stuff. You have to be careful then with adding new features, and you need to think about prior decisions that you made. Maybe they are not as valid anymore. Also, you maybe shouldn't trust all new technologies immediately. And this is not only applying to trusted computing. Anytime you have a new threat model, for example, maybe you open up your website to the public. Previously, it was just for internal employees. Anytime you do something like that, you need to consider old design choices and whether they still make sense. So to conclude this talk, correct code does not necessarily mean it's secure. Side channels can be a real threat. We leaked real cryptographic keys from specific environments. Software caches are also exploitable. Mostly, it's even easier because you can debug the software. And performance and side channel security are sometimes just a trade-off. You want the caches for the performance, but also they leak something. So you need to make a decision here. And for everything you do, try to be aware of the implications of the choices that you make. Mitigating side channels is an open problem. There's a lot of research being done there. And it's not an easy problem because it's very, very easy to overlook something. And with that, I thank you for your attention.
Thank you, Hannes. Do we have any questions? Yeah?
So could you estimate people's approximate geolocation by checking the response time of content distribution networks, right? CDN services. Could you just
That-
like
that-
if you send somebody like a friend request,
Mhm.
they load your and like a CDN network loads your profile picture, and then you check those caches or something maybe.
That could actually work. Yes, that
Okay.
I could see that being a thing. Yes,
This was done
this was done.
against Slack and against Discord.
Interesting.
There was a prototype for Signal. It was a whole thing. There's blog posts.
Great.
Do we have any more questions? If not, then thank you, Hannes.